So in order to start this out today, what we're going to do is we are going to look at these four different molecules. And I've given you what they look like. You don't have to know that yet. But basically, what I want you to do is look at these four molecules as a group, and I want you to draw structural formulas for them, find the molecular weight of each. If you want to, you can Google this, or you can add up the carbons and the hydrogens and the oxygens from the periodic table, find a total molecular weight, and then I'd like you to list the intermolecular attractions present. And then finally, with this information, rank what you think the boiling point is from the lowest boiling point to the highest boiling point. And obviously you can Google this. This is not something that obviously you can't look up in 10 seconds, but if you get more practice at this, you'll be better at tests. Okay, so pause, do this. Okay, so I'm going to assume you did that, and I'm scrolling up here to show you the answers. The first thing I did was, here are the molecular weights for each, okay? So you can see that this, and this are very similar to each other, and this one is really big. It's almost double the size of these other ones, okay? The second thing I'd like you to notice are the intermolecular attractions, okay? This one has dispersion forces, but I'm going to call it medium dispersion. I guess I could have called it low. Medium dispersion, and this one has medium dispersion because they're all about the same size. Now this one also has dispersion forces, but it's going to have high dispersion forces, much higher than the other three. The second thing you'll notice is that these two are polar, so they both have dipole-dipole. So here's a polar portion right here, and here's a polar portion right here. As far as this one, this has hydrogen bonding, and so when you have hydrogen bonding, you also have a dipole-dipole. Okay, and then this one has no other forces. This is just completely nonpolar, and the same with this one. So then I asked you to rank the boiling points. Now, this is what I tell people. Giving you all four of these on a test would not be fair. Okay, I could give you this one, and this one on a test, and you could rank their boiling points. Or I can give you this one, and you should be able to rank the boiling points. But the reason that all four of these aren't fair is because you're not going to be sure whether the dispersion forces are going to be high enough or large enough to be as strong as hydrogen bonding, if that makes sense. So in this case, it turns out that octane has such high dispersion forces, it does end up with a very, very high boiling point. Okay, remember, high intermolecular attractions mean stickier molecules, which mean that they are less volatile, they do not evaporate as easily, and they have higher boiling points, okay? So octane, if you spread it out on a table, is going to last longer on that table than pentane. And like I said, if you're looking at these two head to head, it's no problem. They're both nonpolar. This one's way bigger, obviously has a higher boiling point. Now, if you're looking at these three, it's not going to be a problem because they're all about the same size. And this one has only dispersion, this one has dipole-dipole, and this one has hydrogen bonding. So this one's going to be the lowest boiling point, the second, and the highest boiling point out of these three. But the wild card is, where does this fit in with these three? And it turns out to have the highest boiling point. So we're going to do more practice with this, but that's basically how you start ranking boiling points in organic chemistry.